Hello, everybody. Today we're having the last video of the first chapter of this course, the chapter about constant memory computations, DFAs, NFAs, and perhaps it would be a good time for you to view the introductory video for this chapter, kind of as a summary of everything we've done. But in this video, we're going to talk about communication complexity. And just like streaming algorithms, this is a very active area of research. So unlike some of the other stuff we're doing in this course, both communication complexity and streaming algorithms are very, very active areas of research with lots of beautiful results being derived every year. Communication complexity have many applications in many areas. It's a way to understand a lot of things. And today we're just going to give a taste of it. The motivation is to connect communication complexity to streaming algorithms, and this way also to regular languages. But indeed, communication complexity goes way beyond that. So very directly, communication complexity tries to model one aspect of distributed computing. In distributed computing, the input to a computation is distributed among various parties or many servers, and they want to gather or need to gather to compute some function, and what we model in this in communication complexity is the amount of information they need to exchange. So the focus is about information, about communication, rather than any other aspect of computation. Specifically here, we will consider just two parties, Alice and Bob. But as I said, there are various models of communication complexity, and some of them definitely deal with many parties. And we assume that they want to compute a function f on their inputs. So Alice has the input x, Bob has the input y, and they want to compute f of x, y. We will assume here that x and y are of the same length, but it's not a really necessary assumption. And we think about n as huge. So just sending all of x from Alice to Bob is not a realistic way of communication. So we want communication that's much smaller than that. So Alice knows x, Bob knows y, and they want to compute f of x, y, and they want to exchange the minimal amount of information between them, the shortest messages between them. And again, we do not model here computation cost. Each one of them, on whatever information they have locally, can run with no cost any computation that they want. In the language that we'll define later, they can even compute unrecognizable languages. So whatever function they want to compute, they can do it in a single time step. I would just mention that just like with streaming, the specific protocols that we will see will have very efficient computation. We will not ask you to, or ask Alice or Bob to compute unrecognizable languages, but the impossibilities, and our focus here are going to be about impossibilities, are very strong. So they say no matter what computation you're willing to perform, you will need to exchange many bits. So Alice and Bob communicate with each other. They have a conversation, or as we call it, they run a protocol together. We have Alice, we have Bob. Alice has X, Bob has Y. And every step, one of them is going to send a single bit to the other. So Alice sends a bit, and Bob sends a bit, and they continue. And note that each one of these bits is a function of their input. So Alice sends bits that are a function of her input, and whatever messages were seen till now. So the transcript of the communication till now. So the first message is A of X epsilon, because so far Alice only knows her input. The messages exchanged so far are empty. This is the first message. And then Bob sends a message that a bit that is a function of his own input, and the messages so far. So far, in this example, Bob have seen a 0. And computing this function, it sends a 1. Alice now applies on X, and the messages so far, which are 0 and 1. And Bob sends a message based on Y, and the messages so far, 0, 1, 1. At this point, Alice decides that the protocol is done and sends a stop message. It's a special message sent once. We view it as being external to the protocol. And our convention is going to be, and this is without loss of generality, that the last message before the stop is the function that they want to compute. And indeed, if they compute it, the moment Alice and Bob know what is the function, they can send one more message. So the cost of assuming it is just one more bit of communication. The communication cost is the number of bits communicated. Here it's 4 bits. And we assume that they alternate, and then that they send a single bit each time. As I said, the last bit that is sent is f of xy. Now, this is a very basic model of communication complexity. In particular, this assumption that they alternate, and at every point they send a single message, a single bit as their message, is on one hand without loss of generality, but on the other hand it's very simplified. So it's without loss of generality in the sense that, let's say Alice wants to send a large message, then Alice can send her message, and Bob can send garbage in his own rounds. So the amount of information that exchanged doubles at most. So if Alice wants to send 10 bits, it will take 20 bits of communication. So as long as we don't care about a factor 2, this is without loss of generality. It is a very limiting model, and often we do consider models where messages can be longer. And this is when we want to model not the number of bits that are exchanged, but the minimal number of rounds, or perhaps both, the minimal number of rounds and the length of the bits. And sometimes the rounds of communication are more important than the number of bits. Even from a practical standpoint, sometimes the latency in sending messages is the serious bottleneck, and you can just as well send longer messages. But again, here we are going to do something very simplified where the communication is a single bit. For some of our results, this would not actually make a difference. So formally, a protocol between Alice and Bob for computing the function f is 2 functions. It's the function A that determines the messages Alice sent, and the function B that determines the messages Bob sends. And these messages are always on your input and the bits that were exchanged so far. And at each time, it's a function that tells you either to send a 0 or to send a 1, or perhaps to send a stop. On input xy, we in round 0, the B0 is empty. So far there is nothing that was exchanged. So we can define B0 to be empty. And as long as BR, the message that is sent at round R, is not stopped, we are going to continue. We are going to increment R by 1. And if R is odd, then this is when Ellie sends a message, and her message is going to be BR, which is A of her input X, and the bits that were sent so far, B1 up to BR minus 1. Else Bob sends, it's even around, and Bob sends the message BR, which is B, the function that Bob uses on its own input Y, and B1 up to BR minus 1. And you output BR minus 1. So you stop when BR is stop. And the last message before the stop is BR minus 1. And this is supposed to be f of xy. The number of rounds are R minus 1. We don't count. We only count the 0, 1 rounds. So a protocol for the function f is one when for every x and y, the outcome is going to be f of xy. And now we want to measure the cost of such a protocol. So how efficient it is, and how efficient in what we care about here, which is the amount of communication, how many bits are exchanged. So the cost of a protocol P for F on n-bit strings is the maximum over the inputs x and y of the number of rounds this protocol will run to compute f of xy. So for different inputs, perhaps the protocol runs in different number of rounds, and we look at the input that makes the algorithm run. The protocol runs for the most number of rounds. There are cases in which we care about not the worst case complexity. This is worst case complexity. We look at the worst x and y, the worst behavior, but perhaps on average case complexity. But again, this will be beyond the scope of this very minimal look into communication complexity. So a protocol is efficient or not efficient based on the number of bits that are exchanged on the worst input for every length n. And the communication complexity of f, so now we want to look not at the complexity of the cost of a particular protocol for f, but the inherent complexity of f. This is what we'll do a lot in communication, in complexity theory in general. We want to understand the inherent difficulty of problems. So the communication complexity of f on n-bit strings is the minimal cost, the minimum cost over all protocols for f on n-bit strings. Of course, there are very inefficient protocols for anything. Alice and Bob can just exchange zeros forever and then run another protocol to compute the function. So that's not interesting. We wonder what's the real difficulty of the function. What is the cost of the best protocol? And this is inherent cost. It means that no matter how smart Alice and Bob can be, they cannot exchange less information than the communication complexity of f. So the communication complexity is the minimum number of rounds used by any protocol that computes f of xy over all n-bit strings x and y. So let's look at a few examples. We'll start with the extreme examples. So assume that f is just an arbitrary function. We don't know anything about this function. What is the communication complexity? What is the bound on the communication complexity? What is a protocol that works always for every function? There is always a trivial protocol where Ellie sends her bits in odd rounds. Bob can send his bits in even rounds. In fact, he doesn't really need to send the bits at all. And the moment they kind of complete their exchange, Bob, for example, knows both x and y. And since we said that computation is for free, Bob can locally compute f of xy and just send this bit. So after 2n rounds, they both know each other's input, and the communication complexity of every f is at most 2n. So this always holds. Let's look at the other extreme. Consider the function parity of xy. Parity of xy asks if the number of ones in x and y together is even or odd. So it's the sum of all the bits xi plus the sum of all the bits yi modulo 2. This is the parity function. What is the best protocol for computing parity? Here there is a very efficient protocol. Alice just sends the parity of her own bits, so sum of xi mod 2. Bob adds to this bit, to this b1, it adds the parity of its own bits. So it's b1 plus sum of yi's of all its own bits, modulo 2. And this is b2, and it's not hard to show that b2 is exactly the parity function. So b2 is what they wanted to compute. So Alice in the third round can just send stop. So the communication complexity for parity in this model is 2. In fact, this is minimal because unless a function only depends, for example, on Alice's input, and then Alice can just send the value in the first round, we need 2 rounds. If there is some dependency on Bob's input, then Alice needs to send something and Bob needs to send something. So 2 is the minimal. So the range of communication complexity is between 2 and 2n. And this is the range in which we analyze things. And 2n, in general, n is trivial. We think about n as very large. We are very unhappy with protocols that require you to exchange about n bits. Let's give an example that is not extreme in either way. And this is the majority. So we ask, what is the most frequent bit in xy? Are there more ones or more zeros in the concatenated input of both parties? What is a good protocol for majority? Well, a protocol for majority is for Alice to send the number of ones in her input, and then Bob can compute the number of ones in his own input and add them together. Now Bob knows the number of ones in the concatenated input, and we assumed, although it's not very important, that they know the length of both inputs. It's n for both of them. So if nx plus ny is greater than n, then the answer is 1, and otherwise it's 0. So the communication complexity of majority is order log n. They need to exchange 2 log n bits. And let's look at the last function that we'll care about, and we're actually going to look at it quite a bit, which is equals. So equals of xy is 1 if x equals y. Looks arbitrary, but in fact it is a very, very natural function. So assume both Alice and Bob as a copy of a document that is supposed to be the same, and they want to check if it's indeed the same, if it was got corrupted on one side or not. So they want to run this protocol. It's a very natural question. What is a good protocol for computing equals? So definitely it is at most 2n, because we said that it is at most 2n for any function. But can we do any better? So let's table this question about equals and see why did we talk about communication complexity now? What's the connection to streaming and DFAs? So we want to connect languages to functions, because for DFAs, we talked about recognizing a language, and we want to connect this to computing a function. So let's consider a special kind of function, which is FL, defined for L, which is the function that says 1 if when you concatenate x and y, it is a word in L. So FL of xy is 1 if and only if x concatenated with y is in L. And in fact, all the functions we saw so far are of this form. So if L is x has odd number of ones, then f of L is the parity function. If L is x has more ones than zeros, then FL is the majority function. And if L is the language of inputs XX, so x repeated twice for some x, then the function is equals. So 3 concrete functions we looked at are all essentially of the same form. So let's see with this notation, what can we do? What can you say? So here is the theorem. The theorem is that if L has a streaming algorithm using at most S bits of space, then the communication complexity of FL is at most order S. So a streaming algorithm can turn into a communication complexity protocol. And how would we do that? The same way we do all reductions of this sort. When one model we want to say that one model reduces to the other, we'll do it with the simulation argument. So we'll show that this protocol can simulate the streaming algorithm. And the idea is the following. Alice can run the streaming algorithm, A, on the first bits of the input. So on X, right? The streaming algorithm gets the bits of XY 1 bit at a time. So it starts by reading the bits of X. And Alice knows all of X. So Alice can simulate in her own mind, in fact, by one computation, so for free, can simulate what the algorithm A would do when it reads X. At the end, when it finished reading X and it's just about to read Y, Alice captures the memory content of A, which is an S bits of space. A is a protocol that uses S bits of space, and so after reading X, it has some content, and it captures this content and sends it to Bob. So this is the message of Alice. Here I'm kind of describing it as Alice sends a big message, and this is the case where Alice can send it bit by bit, and Bob sends garbage at the beginning, so we don't care. Now Bob can continue simulating A, because all Bob needs to know about X is what's the state of A when it completed reading X. Recall that in streaming, it's not that you can access X again. You cannot access bits that you already seen. Once it's seen, it's gone. The only thing that determines the rest of the computation is what happened at this very moment. What is the memory content at this very moment? And therefore, Bob can continue simulating A now on Y. And when it gets the output of A, so at the end of the simulation, it sees that A accepts or rejects, and it sends this bit to Alice. So this is the communication protocol, and it is order S. So Alice sends S bits, and in this kind of model, they spend 2S bits. And so it's probably about 2S plus order 1, but who cares? Well, perhaps somebody cares, not me. So that's one connection between streaming and between communication complexity and streaming. Let's push on it a little bit more. So the theorem was that if L has a streaming algorithm using at most S bits of space, then the communication complexity of FL is at most order S. And the corollary is that for every regular language, the communication complexity of FL has to be order 1. Because the language is regular, it means that there exists a DFA, and once there exists a DFA, it means that there exists a streaming algorithm that uses order 1 memory bits. And once there is this streaming algorithm, there is also a communication complexity protocol that exchanges order 1 bits. So that's one corollary. An example is that the communication complexity of parity is order 1. We know it's very easy directly, but we can also deduce it from the fact that the corresponding language is regular. Another corollary is that the communication complexity of majority is order log n. Because there is a streaming algorithm for this language, X has more ones than zeros with order log n space. We've seen it in the last video. So this is another way to argue the communication complexity of majority. What about the communication complexity of equals? So this will be a more interesting corollary of this reduction. So let's discuss that. So communication complexity of equals, we're going to show that it is theta n. So definitely it's easy to say that the communication complexity is order n because the communication complexity of every protocol is at most 2n. But what this theorem says is that in fact you need a linear number of bits to exchange in order to learn equals, or even more accurately, it will show that every protocol for equals need at least n bits of communication. So no communication protocol can do much better than just a trivial thing where Alice sends her input to Bob. And the corollary is, well, first that L of WW is not regular. And moreover, that every streaming algorithm for L needs Cn bits of memory for some constant C larger than 0. So it means that not only communication complexity requires a lot of bits, the streaming complexity is also high. You don't have a streaming algorithm that uses less than a linear number of bits, which again is trivial up to a constant. So I want to again point, and I'll do it several times in this course, that again we're using reductions not in the algorithmic sense, but in the complexity sense, complexity theoretic sense. We use it to show lower bounds. So we know that a streaming algorithm implies a communication complexity protocol. And in the previous two corollaries, we said, okay, there is a very good streaming algorithm, and this implies a low communication protocol. But here we're saying the opposite. We say there is no good communication protocol. Every protocol needs to exchange a lot of bits. And this means that every streaming algorithm needs to store a lot of bits. Because if there was a streaming algorithm that would store a few bits, then there would be a communication algorithm that would exchange few bits. And since this is impossible, then this is impossible. This is kind of the complexity version rather than the algorithms version. So let's try to prove it. And we're going to use one of the very, very basic methods of arguing about communication complexity. There is a huge and beautiful literature with a lot of techniques. This is kind of the very first technique. It has names and definitions, but we'll do it directly here and not to burden you with the unnecessary notations. So what we want to do is consider all possible ways in which A and B can communicate. And we're going to define the communication pattern or the transcript of communication. So the communication pattern of a protocol on input XY is the sequence of bits that Alice and Bob send. So here, what is the communication pattern? It's just sequence 0, 1, 1, 0. Again, we can call it transcript as well. And now, let's assume, for the sake of contradiction, that there is a communication complexity protocol for equals that only requires n-1 bits, so less than we said. If that's the case, then we can show that there are at most 2 to the n-1 possible communication patterns of that protocol over all pairs of inputs XY that have n bits each. So whenever you exchange n-1 bits, there are 2 to the n-1 possible ways of setting up these bits. And we can assume here that they exchange exactly n-1 bits. So if there is a protocol that uses at most n-1 bits, then there is a protocol that uses exactly n-1 bits. If we wanted the protocol to run for less potentially bits, then we will need to count more possible communication patterns, but it will still be less than 2 to the n. But forget it. We can assume that the protocol runs in exactly n-1 bits, because it can always continue by sending garbage until they count n-1 messages. And therefore, there are 2 to the n-1 possible communication complexity patterns. What does this mean? It means that there exist X and Y that are different, such that XX and YY produce the same communication pattern. When Alice and Bob, as both of them have X as input, their pattern is P, and whenever both of them have Y, the pattern is P as well. Why is this correct? This is the pigeonhole principle. So the number of pairs XX is 2 to the n because the number of X's is 2 to the n. And if there are more pairs than communication patterns, there should be 2 pairs, XX and YY, that produce the same communication pattern. So that's the claim. We don't see yet how it helps us, but very soon it will. It will when we will consider the communication pattern of XY. So what is the communication pattern of XY? It is P as well. And let me try to argue that, and you can convince yourself as well. Essentially, the proof will be by induction. We will say that the communication pattern in the first I rounds is the first I bits of P, and we will continue as well. So assuming that, for the empty pattern, all patterns are exactly the same before they start communication. And now let's imagine that we proved it for I minus 1 and we want to prove it for I. And let's say, without loss of generality, that it is Alice's turn. If it's Alice's turn, Alice has the input x. And she sees the same communication that pattern that is produced on the protocol that has XX, right? We assume that XX has communication pattern P, and we assumed in the induction that so far the communication pattern on XY is also like P, is consistent with P. Now at this point, Alice's next bit only depends on X and the pattern she sees so far. So she will not be able to distinguish XX from XY, and she will send the same bit on XX and XY. So the next bit of communication is going to be still the same between XX and XY. Similarly, it's going to be the case for Bob. If it's Bob's turns, Bob similarly will not be able to distinguish YY from YX. Bob sends a message that is a function of Y and the bits that it's seen so far. So if by induction, so far it's seen the bits of P, it will send the same thing on YY and XY. Not very complicated, you can try to prove it by yourself. So Alice and Bob are going to have the same communication pattern on XY and XX, and recall that the output is the last bit in the communication. So they're going to output the same bit on XY and XX. But they're not supposed to output the same bit because equals of XY is 0 and equals of XX is 1. So the protocol makes a mistake on one of them. And this is a contradiction because we assumed we have a protocol for equals that uses n-1 bits of communication. So this is a contradiction. It's a new thing for you, but it's a very standard in communication complexity, and it's a proof that fits on a single slide. This is, again, a very devastating state of affairs, or at least looks like a very devastating state of affairs, because equals, again, it's a very, very natural protocol that we want to run in a distributed setting. I gave you an example. There are other examples. And we see that there is nothing non-trivial here. And similarly, there is nothing non-trivial for streaming, which is, again, very devastating. So what will save us here, as it saved us before, is randomness. And again, I'm going to hint of a randomized protocol for equals that is going to do much better. So the protocol is going to compute equals, not always, but with very high probability, with probability 99.9%. And this could be extended as much as we want. So it can make an error with probability 2 to the minus 100. And with this probability, Alice's and Bob's computers can also fail, and with much higher probability, they can fail for other reasons. And so this seems very legitimate. And the point is that this protocol, instead of exchanging n bits, is going to exchange order log n bits, so much smaller. So let's think about a natural protocol for equals. A natural protocol would let Alice send some bits of her input. For example, it says, okay, you know, my 100th bit is 1. What's yours? Bob looks and says, oh, no, it's 1 as well. Says, okay, but what about your 20th bit? Mine is 0. Mine is 0 too. And this protocol will take a lot of iterations, and no matter which order they're going to look at their bits, as long as it is a deterministic. And because if X and Y are different in a single bit, it's really hard to deterministically find which bit it is. It can be the last bit. And even if it was a randomized approach, I'm giving you a random bits every time, if they're different in a single bit, it will take you a linear amount of time to discover it. So this is where we use error correcting codes. If Alice encodes her input with an error correcting code and Y encodes it with an error correcting code, then now what we have is a situation where if X equals Y, the encoding didn't change it. The encoding of two strings that are the same is still the same. But if X is different than Y, even in a single bit, then now after applying an error correcting code, they will be different in many, many bits. In a constant number of bits, for example. That's the point about error correcting codes. Error correcting codes want to have a lot of robustness. If some bits get corrupted, we'll still get the right message. So every two messages are going to be different in many bits. Let me instance, and then by sending a few random bits, Alice can really determine if it has the same file with very good probability. Let me instantiate it with a particular error correcting code based on primes. So the modulus of X and Y on various primes. So here is the protocol when we instantiate it. Alice picks a random prime number, P, between 2 and n squared. And there are many such primes. She sends P to Bob, and she also sends X modulo P. This is a number between 0 and n squared, which means that it takes order log n bits to send it. Bob checks whether Y equals X modulo P and sends the output bit. If Y equals X modulo P, then they think that perhaps they have the same file. Otherwise, they assume that it's not the same file. And the point is that there are at most logarithmic number of primes on which X and Y that are different are going to agree. And there are many more primes between 2 and n squared. Now this can be amplified either by choosing several primes, a constant number of primes, or by choosing primes in a larger domain. But in fact, the first method is better. Again, this is not supposed to be something you completely internalize. It's kind of just an example of how a randomized algorithm can work. And indeed, both for streaming and communication complexity, randomness is very, very powerful. So let's kind of meditate about what we've seen here. We've seen communication complexity, which is a powerful tool. We just seen the tiny demonstration. It applies to a lot of areas. You can prove a lot of areas, interesting results through communication complexity. Furthermore, communication complexity, streaming algorithms, and regular languages are all connected. And we've seen our second example of how randomness could be a very useful resource of computation. So usually we think about time and memory as resources of computations. And so far, we also seen communication as a resource of computation in the distributed setting, and randomness as a resource of computation. And with that, we're finishing the first chapter of our course. Thank you.